Swayam Prabha. Digital India. Educated India.
Good afternoon. So, in today's class, we will be capturing a few more review concepts, and with this capture of review ideas, once this is done, then going forward we will move into formal acoustics area, and we will start with one-dimensional wave equation. But at least in today's class and maybe one more class, we will be essentially doing a review of some of the concepts which we will be using frequently in the area of acoustics. So, the first concept I would like to talk about is having a very brief overview of what is an overdamped system, what is a critically damped system, and what is a underdamped system. And I'll explain that in context of a spring mass damper system, and hopefully with that illustration these terms overdamped, critically damped and underdamped will become clear. So, let's consider a dashpot, and then I also have a spring. So, the dashpot viscosity is C, spring constant for the stiffness is member is K, and both these elements, they are connected to a rigid body mass which can move on a frictionless surface. So, now let us assume that I am trying to perturb this by a small displacement x. So, from our previous classes we know that in such a situation the system is governed by a differential equation of this type, mx double dot, which is mass times acceleration plus viscous coefficient times velocity plus stiffness times displacement equals 0. And to solve this equation, if I assume that x is some constant times exponential of est, where s could be a complex number, and if I plug this in my differential equation, what I get is m s square plus C s plus k times x naught E s t equals 0. And if this equation has to hold true at all times for all frequencies, then the only natural conclusion we can draw is, for this equation to hold true, this term ms square plus cs plus k should be 0. What that means is, so I will write that ms square plus cs plus k equals 0. Now, we know what is m, it is a physical quantity, mass of the object. We know c, it is again a physical quantity, viscous coefficient of the damper, and we know k, which is the stiffness of the spring. So, this is a quadratic equation. It is a quadratic equation in S. So, I solve for S. So, S equals minus 2C, I am sorry, it is minus C plus minus, and then I have C square minus 4 km, and then I divide the whole thing by twice of mass, which is minus C over 2m plus minus, and then I move mass under the square root sign. So what I get is C over 2m square minus k over m. So that is my S, and S we know, we call S is complex frequency. So now we will come up with 3 scenarios. So first is case 1, and in this case this term is the term under the square root sign is larger than 0. In other words, C over 2m square is greater than k over m. And when that happens, what it essentially means is that S is a purely real negative number. So there is no imaginary component to S, and which in turn means that for a system where you have C over 2m square is greater than k over m, there are no oscillations in the system. And such a system where C over 2m whole square is larger than k over m, such system is called overdamped. Overdamped system. Then there is another case. So case 2 would be C over 2m whole square equals k over m. In that case, my S will be minus C over 2m. Again, C is a real number, m is a real number, so S is a real number and it is also negative. So once again, in this case, there are no oscillations happening in the system, and the system is called critically damped. Critically damped system. A good example of a critically damped system is sometimes in the doors which have dampers, so that the door closes silently without creating a lot of noise. Sometimes those dampers are tuned in such a way that the whole system is critically damped. Some other examples where people use critical damping is these military guns where the barrel coils back when the system is being fired. So once you have a charge coming out of the barrel recoils, and that recoil phenomena is critically damped. So in critically damped system, the response, as you may have studied in your previous courses, would be something of this nature: A plus B t times exponent of minus omega naught t, where omega naught equals C over 2m. And then we have a third case, so it's case 3, where C over 2m whole square is less than k over m. And in this case, S is a complex entity. So it's a complex number. And once you have a complex number, what that also means is that the system is going to oscillate, because a part of a component of the complex frequency is imaginary in nature, and that will that essentially implies that the system will oscillate. So that is there. So let's plot some of these performances. So if I have a system and I'm trying to plot its displacement, if I perturb a spring mass damper system, single degree of freedom, and if I perturb it, and along time axis, the horizontal axis is for time and the vertical axis is for displacement. Then a critically damped system would be the fastest to decay. So, this is critically damped. Critically damped. Then an overdamped system will also decay fast, but not as fast as a critically damped system. So, it will be fast, but it will be a little slower. And note that in both these situations, the oscillations are not happening. So, this is an overdamped system. And then finally, you have an underdamped system where there will be oscillations, and the magnitude of all these oscillations will slowly decrease, will decrease with time in an exponential way. So, this is my underdamped system. So, that covers the review of different types of damping: overdamped systems, underdamped systems, and critically damped systems. So, now we will move on to the next concept in the class, and this is what we call a pole zero plot. So, what we are going to talk about, pole zero plots. So, any transfer function, and we had talked about transfer function in some of the earlier classes. So, if I have a system, there is an input signal going into the system, and then I am observing, and I consider that observation as an output of the system. And if I take the ratio of output and input, and if a system is linear, then that ratio is called a transfer function. And this transfer function can depend on the natural frequency, not natural frequency, the frequency of the ingoing excitation, and it will also depend on the element properties of the system. So, any transfer function can be, it's a ratio, and because it's a ratio, I can decompose it into roots of the numerator and roots of the denominator. So, it could be S plus Z1, S plus Z2, S plus Z3, and so on and so forth, depending on how complex the transfer function is. And I can also decompose the denominator into its, in terms of its roots. So, S plus P1, S plus P2, S plus P3, and so on and so forth. So, here Z1, Z2, Z3, these are roots of numerator, and they are called zeros. They are called zeros because at S equals Z1, Z2, Z3, the transfer function goes to an identically zero value. Also, the roots of denominator P1, P2, P1, P2, P3, they are called poles. And at these values of S, that is, which is complex frequencies, so HS goes to 0 at zeros, and HS goes to infinity at poles. Actually, I made a small error here. Actually, these should be S minus Z1, S minus Z2, minus Z1, S minus Z2, S minus Z3. Similarly, here I should be having S minus P1, S minus P2, and S minus P3. So on and so forth. So when I am, so let's do an example. So we'll consider transfer function H, which is a function of function of complex frequency S, and it is expressed as S plus 3 over S square plus 7S plus 10. So this is S plus 3, and then I can factorize the denominator, so it becomes S plus 2 times S plus 5. So my zeros are S equals minus 3, which comes from the numerator, and the roots of the denominator will give us the poles. So my poles are S equals minus 2 and minus 5. So if I plot this on a complex plane, that's my real axis, this is my imaginary axis. So 1, 2, 3, 4, 5, and I will designate a 0 as a circle. So at minus 3 I have a 0, and then I can designate a pole as an x. So at S equals minus 2 I have an x, which is a pole, and at S equals minus 5 I have another pole. So I know that S equals sigma plus j omega. So on the real axis I am plotting sigma, and on the imaginary axis I am plotting omega. We'll do another example, and in this case the transfer function is Hs equals S square plus 4 over S square minus 6 S plus 25. So I can decompose the numerator into its roots. So that is S plus 2j times S minus 2j, and then the denominator is S minus 3 plus 4j times S minus 3 minus 4j. So my poles, which are designated as x's, are roots of the denominator. So it's 3 plus 4j, and the other pole is 3 minus 4j. And my zeros, designated as O's, are minus 2j and 2j. So if I have to plot them on a complex plane, that's my real component, this is my imaginary component. So my zeros are located along the imaginary axis, plus and minus 2j. My poles are located in the complex plane, as I am going to just plot just now. So it is 3 plus and minus 4j. So let's say this is 4. So I have a pole here, and I have another pole at 3 minus 4j. minus 4, and then I have plus 4 on the positive side. So this is the representation of my poles and zeros for this transfer function Hs. So now that we have understood how to identify poles and zeros of transfer functions, we want to go to the next step, and which is plotting these transfer functions. And I can plot the transfer function, and it will have a phase component, and the other component will be a magnitude component. So that is what we are going to do. The purpose of making these plots is that I have a graphical representation of how Hs is varying as omega is changing. So typically, so let's say I have Hs. So a phase plot or a magnitude plot will be a plot of H when S equals j omega. So I don't put a real part in S, and I just plot H as a function of j omega. So my horizontal axis is going to be omega, and my vertical axis is going to be the value of H, the magnitude of H or the phase of H. So let's say Hs equals S plus 3 over S square plus 5S plus 10. So we had broken this earlier as this S plus 3 over S plus 2 times S plus 5. So now if I have to do a phase plot or a magnitude plot for H, I set S equals j omega. So then my H j omega becomes 3 plus omega j over 2 plus omega j times 5 plus omega j. Now what we see here is that H is a function of, is a product of 3 individual small transfer functions. Why is that? So I'll just write down H1 times H2 times H3, where H1 is 3 plus omega j, H2 is 1 over 2 plus omega j, and H3 is 5 1 over 5 plus omega j. So, and that is H j omega. And we know from the mathematics of complex variables that if I have a relation for H in such a way, then magnitude of H j omega is basically magnitude of H1 times magnitude of H2 times magnitude of H3, and also the phase of H j omega. So the phase of H j omega is basically phase of H1 plus phase of H2 plus phase of H3. So in this case the phase of, so again, so magnitude of H is basically magnitude of H1, and H1 is 3 plus omega j. So magnitude of H1 is 3 square plus omega square times magnitude of H2. So I'll write down that times 1 over 2 square plus omega square, the whole thing under square root. And then similarly I have magnitude, I have to write down magnitude of H3. So it is 1 over square root of 5 square plus omega square. So now we have a relation, and I can plot the magnitude component of H in terms of omega. Similarly, the phase component I can plot, and I know from complex variable theory that the phase of H is basically a summation of phases of H1, H2 and H3. So that is what I will do. So phase of H1 is tan inverse omega over 3 minus tan inverse omega over 2 minus tan inverse omega over 5. So I have now two relations. I can use these two relations to develop a phase plot and a magnitude plot for H. So in a quantitative sense, this is how the magnitude plot for this particular transfer function looks like. So what I am plotting is magnitude of H. On the horizontal axis I have omega, and this function, it peaks at 0, and the value of H at 0 is about 0.3, and then it asymptotically goes to 0 as omega goes to infinity. And the phase plot, again on my horizontal axis I am plotting omega, and my vertical axis I am plotting phase angle, and the phase plot looks something like this. These are asymptotes at pi over 2 and minus pi over 2, and my phase plot looks something like this. So it's an anti-symmetric curve, anti-symmetric along the vertical axis. The magnitude plot is a symmetric curve, symmetry being along the vertical axis. So this is how we can construct phase and magnitude plots for transfer functions by step 1, decomposing the whole transfer functions into its poles and roots and factors associated with those poles and roots, and B, if we are trying to plot magnitude, then we find individual factors themselves and multiplying them, and if we are trying to find the phase, then we find phase relations for individual factors and then just adding them up. We will do another concept which is called a Bode plot. So right now what we did was we plotted H on a linear axis. We plotted the magnitude of H on a linear axis. The horizontal axis was linear, and also the vertical axis where magnitude was being plotted, that was also linear, and same was true for phase. Now what we have another concept, and it's called a Bode plot, and Bode plots are essentially graphical depictions of transfer functions when S equals j omega. So they are graphical depictions of transfer functions at S being equal to j omega, and more specifically they are asymptotic behaviors. Further, when we are plotting Bode graphs, then we essentially use logarithmic scales on both horizontal and also the vertical axis when we are plotting the magnitude, and when we are plotting phase, the vertical axis remains a linear scale, but the horizontal axis still is a log axis. Plots. So there can be two types of Bode plots. One is magnitude plots, and this is basically a plot of 20 logarithm on base 10 magnitude of h j omega versus on the horizontal axis we have log of omega. Again, so log 10, and the second Bode plot is a phase plot. And here we are plotting the phase of h when s equals j omega, and on the horizontal axis we have log 10 omega. And these plots are basically plotted in such a way that we have asymptotic representations. Asymptotic representations. So essentially we are trying to plot the asymptotic behavior of magnitude and asymptotic behavior of phase of h as omega is changing. In case of the magnitude plot, we are plotting asymptotic behavior of h on a log scale in the vertical axis and also on a log scale on the horizontal axis. For phase, the vertical axis is still linear, but the horizontal axis is log scale. The point, the central point when we are plotting these Bode plots is that we are focusing on asymptotic behavior because these plots very quickly help us generate a curve which we can look and get a feeling of the approximate behavior of the system. And once we have an approximate feeling for the approximate behavior of the system, then we can use that information to validate our understanding of the model which we are trying to analyze. The other point I wanted to make is that some thought as to why we are using 20 times logarithm of h j omega, especially when we are plotting the magnitude plot. So this is because it's not directly a representation of the magnitude itself, but rather it's a representation of the energy contained in the system. So what do I mean by that? So let's try to understand it a little bit more at a detailed level. So typically when we plot h in physical systems, I have a signal going in and I have a signal coming out. So let's say I have a acoustic system, it's getting excited by some signal, let's say it's an electrical signal. So I try to monitor that electrical signal in terms of voltage. So my input parameter is voltage, and my output parameter, in case it's a microphone or some other displacement sensor or velocity sensor, at the end of the whole transduction process, I end up measuring some more voltages. So my input is a voltage and my output in a lot of cases is voltage as well. Or in other cases it could be current and current, or combination of voltage and current. V square, which is square of voltage, is essentially proportional to energy. For instance, across a resistance, if I have voltage V, then the energy dissipated is V square over R. Similarly, I square is again proportional to energy in a general sense. again if I have the example of a resistance and the current going through it is I and the value of resistance is R, then energy dissipated or power dissipated is I square R. So when I am taking ratios, so let's call this a decibel, and this is defined as 10 times logarithm of ratio of energies. So as energy is directly proportional to V square and current is directly proportional to, energy is also directly proportional to I square. So I can, so at this point of time, now that we have seen that energy is proportional to the square of voltage or energy is proportional to the square of current, we introduce a term called decibels. And decibel is essentially defined as 10 times log of ratio of energies, and the log is on log 10 scale. So what that means is that it is essentially log 10, and ratio of energies could be V2 square over V1 square, and I have to take the magnitude of it as this is log. And I can similarly have a relation for current also. Now note that V2 and V1 are functions of j omega. They can be functions of j omega. So when I have a square relationship, what this essentially means is that it is 20 log 10 of magnitudes of V2 over V1. So therefore, so similarly, so when we are plotting transfer functions, because they are also ratios of whatever is going in and whatever is coming out. So I have, if I am converting transfer functions on a decibel scale, then what I get is decibels equals 20 log 10 of h, which can be a function of j omega. So as we plot 20 log 10 j omega, h j omega on a y space, so on the vertical axis we are plotting on a log scale, and on the horizontal axis why we are plotting on a log scale is because typically the range of frequencies for acoustics problems, they can start from 20 hertz or maybe even sometimes less than 20 hertz, and then they can go up to tens of thousands of hertz. So it's a wide range, so it's much more convenient to use a log scale on the horizontal axis. So we were talking about Bode plots, and we had said that these plots could be of two types: magnitude plots and phase plots. So now we will see how to plot, how to construct these plots. So as we had discussed earlier, any transfer function could be decomposed into its factors of the numerator and factors of the denominator. So let's do that. So it is, so this is a general transfer function, and then on the denominator I have poles, so now what we will do is we will, as step 1, construct a Bode plot for a transfer function which is made up of only a factor of the numerator, and in another case it is only a factor of the denominator, and see how it behaves, and then we can try to develop an approach through which we can combine plots of different factors. So let's consider a transfer function s plus z, z implying it's on the numerator and it relates to a 0, and I will construct a magnitude plot for this. So, you have to construct a magnitude plot. I have to convert this into decibels, which is, as we had explained earlier, is 20 log on scale 10 magnitude of AHS, where H equals j omega, which is 20 log 10 z plus j omega. And as we mentioned earlier, we have to develop a plot which reflects the asymptotic response. There will be two asymptotes for this relation. So, asymptote as omega tends to infinity, omega tends to 0 is 20 log z, and asymptote as omega goes to infinity is 20 log omega. So, I will plot these. So, my vertical axis, as I had said, is on a decibel scale. My horizontal axis is on a log scale. So, I am plotting log omega on the horizontal scale. On the vertical scale, I am plotting decibels, and I am plotting decibels for the transfer function H S as S equals j omega equals j omega plus z. We had seen that as omega goes to 0, the value of dB tends to 20 log z, and as omega goes to infinity, the value of dB goes to 20 log omega. So, these are the two asymptotes. This is the low frequency asymptote, and this is the high frequency asymptote. So, the low frequency asymptote is converging to a straight horizontal line 20 log z. So, let us say that value is 20 log z. See, and the low frequency asymptote is a horizontal line, and that is my low frequency asymptote. And my high frequency asymptote is 20 log omega, and it cuts the high frequency asymptote cuts the low frequency asymptote at omega such that log omega equals log z. So, at this line, my high frequency asymptote cuts the thing. Also, so this is my high frequency curve. High. Also, the slope is 20 dB per decade, and we had explained earlier a decade is the space between two frequencies which are off by a factor of 10. So when omega increases, and let's say we are starting from omega equals omega 1 to omega equals omega 2, where omega 2 is 10 times omega 1, then this number goes up by in such a way that the slope of this line is 20 decibels per decade. So this is my, again to reiterate, the black dotted line is my low frequency asymptote, the red dotted line is my high frequency asymptote. The asymptotes cut at an important point which corresponds to omega such that omega is where omega equals z or log omega equals log z. So I have a high frequency asymptote red line, low frequency asymptote black line, and the combined line I will draw is the green line. So this is my total response curve. So my response curve for transfer function Hs, where S equals j omega equals j omega plus z, where z is the 0, is this green line. What this line tells me is that as long as my omega is less than z, so in this region, the low frequency asymptote is going to dominate. So and when my omega exceeds z, then the high frequency asymptote is going to dominate. So my total response curve is this green line, which is a combination of low and high frequency asymptotes. So what I have drawn here is a response curve, a Bode plot for magnitude of a very simple transfer function, where transfer function is essentially z plus j omega. So now we will draw another transfer function h j omega, or actually we will start from s. So hs equals 1 over s plus p. So remember, we can decompose a very complex transfer function into a bunch of simple factors, s plus z1, s plus z2, s plus z3, which all go in the numerator, and in the denominator we can decompose it as s plus p1 times s plus p2 times s plus p3, and so on and so forth. So what here I am doing is I am going to plot the Bode plot for a very simple transfer function hs, which equals 1 over s plus p, such that s equals j omega. So this becomes h j omega equals 1 over p plus j omega. So again, I have to draw asymptotic curves because I have to develop an asymptotic response. So asymptote as omega tends to 0 gives me dB becomes 20 log of this whole relation is 20 log 1 over p is basically minus 20 log p. And asymptote as omega goes to infinity gives me, in decibels if I have to do that, is 20 log 1 over omega equals minus 20 log. So now if I have a transfer function which has only a pole, then this is how the asymptotes of the transfer function are. And now I will plot it. I have a horizontal axis on which I am plotting logarithm. Bear in mind, these are all log to the base 10 omega. and my vertical axis I am plotting decibels, and I am going down because both these are negative numbers. So my low frequency asymptote, I will draw a black line, black dotted line. This is my low frequency. And the y-intercept of this is minus 20 log p. And the high frequency asymptote I will draw in red, and this has a slope of minus 20 dB per decade. Again, I will draw it as a red dotted line. So this is high frequency asymptote. Frequency asymptote. The slope is minus 20 decibels per decade. And the combined response, so before I talk about combined response, the intersection point corresponds to a value of omega when omega equals p. So this is log of p. So this is my intersection point. So my combined response I will plot in green is for low frequencies below omega equals p, my low frequency asymptote is going to dominate, and for high frequencies, the high frequency asymptote is going to dominate. So this is my combined curve for transfer function, which is expressed as Hs equals 1 over S plus P. So once again, I have a low frequency component, which is this part, and I have a high frequency asymptotic response, which is this part. The slope is minus 20 dB per decade. The breakpoint corresponds to logarithm of p, where p is this entity, and the horizontal flat curve is basically a straight line in cutting the y-axis at minus 20 log p. So using this approach, so we have seen that a complex transfer function can be expressed as a sum of as a bunch of products on the numerator and also a bunch of products in the denominator. Now we have seen how to construct plots, Bode magnitude plots for each of these numerator components, and also we have seen how to construct magnitude plots for each of these denominator components. So now the next step would be that you synthesize all these individual plots into one single plot, and that will be the overall Bode magnitude plot for the whole transfer function. We will illustrate that through an actual example. My transfer function, let's say, is Hs equals S plus 2 times S square plus 10S plus 109, which is equal to, so now I factorize the denominator, and what I get is S plus 2 over S plus 3 plus 10j and S plus 3 minus 10j. So now what I do is S equals j omega. So my H, which is a function of omega, becomes 2 plus j omega over 3 plus 10j plus j omega times 3 minus 10j plus j omega, and this I can write it as h1 omega times h2 omega times h3 omega, where h1 equals 2 plus j omega, h2 equals 1 over 3 plus 10j plus j omega, and h3 is 1 over 3 minus 10j plus j omega. So I have expressed a complex transfer function such as h in terms of three simple transfer functions h1, h2 and h3. My next step will be to construct Bode plots for h1, a Bode plot in magnitude for h2 and a Bode plot in magnitude for h3. And then I will sum these Bode plots up, because when I take a logarithm of h1, it's essentially a logarithm of h1. If I take a logarithm of h, it is same as log of h1 plus log of h2 plus log of h3. So it's a valid mathematical exercise to construct individual log plots for h1, h2, h3, and then sum them up, and that is my total Bode plot for the entire system. So we will construct a Bode plot for h1. So we know that h1 omega equals 2 plus j omega, 2 plus j omega. So limit as omega goes to 0, I'm essentially developing an asymptotic response for h1 j omega is 2. So my decibels is 20 log 10 of 2 is about 6.02, and then my limit as omega goes to infinite for h1 is basically omega. So my decibels is 20 log 10 of omega, and my breakpoint so before I talk about breakpoint, this is going to give me my low frequency asymptote, this will give me my high frequency asymptote, and the breakpoint where these two asymptotes will cut each other will be such that omega equals p, that is omega equals 2, or log omega equals 0.301. So now I plot my low frequency my Bode plot for this function h1. So my low frequency asymptote, I will do it in black. The y-intercept is 6.02. This is my log omega. On the vertical scale I have decibels. And my high frequency asymptote, which has a slope of 20 decibels per decade, is the red dotted line, and this breakpoint corresponds to log of 2. And my overall curve for h1 will be this green line. So this is the plot for h1. Now I will draw a plot for h2. So h2 we have seen in terms of j omega is this whole term 1 over 3 plus 10j plus j omega. So it's 1 over 3 plus 10j plus j omega. So limit as omega goes to 0 for H2 j omega is 1 over 3 plus 10j. So in decibels, this term goes to 20 log magnitude of 1 over 3 plus 10j is basically 10.44. Basically, I can find 3 square plus 10 square, that gives me 109, take its square root, find the log of it, minus of that, and I get, so this number is minus 20.37. And then similarly, limit as omega goes to infinite, and this is a high, will give us a high frequency response, is H2 j omega, that will go to 1 over j omega. So my decibels will be basically 20 log 1 over j omega is minus 20 log omega. So my Bode plot, my horizontal axis is log omega, vertical axis is in decibels. My low frequency line is going to be again a straight line cutting the y-axis at minus 20.37, and my high frequency asymptote is again straight but slanted line of slope minus 20 dB per decade. Slope is minus 20 dB per decade. And my overall response is going to be this green line, and the break point is going to be such that this is log of 10.44, where 10.44 is the magnitude, as we had seen, of 3 plus 10j. I can do the same exercise for H3s. So my H3 is essentially 1 over 3 minus 10j plus j omega, 1 over 3 minus 10j plus j omega, and my Bode plot will be identical. So this is my Bode plot for H2 j omega, and when we do all the math, we will find that the Bode plot for magnitude for H3 j omega will be same as this particular plot, because the magnitude of the denominator does not change with the change in sign here. So I have constructed a plot for H2 and H3, and I have constructed a plot for H1 j omega. So my next step is to construct a final plot. So H of j omega which is essentially a sum of plots for H1, H2, H3. So if I have to construct a Bode magnitude plot for H, it is essentially a sum of Bode magnitude plots for H1, H2 and H3. And that curve looks like something like this. So initially I have a horizontal line, then I have a upward sloping segment, and then I have a downward sloping segment. The breakpoints, my horizontal axis is log omega, my vertical axis is on the decibel scale. The breakpoints are at log 2, the second breakpoint, as you have expected, is going to be log 10.44, and the y-intercepts are going to be minus 34.72, and the other peak, this peak point is going to be minus 20.37 decibels. So this is my asymptotic response, which corresponds to transfer function h, which is a product of 3 individual transfer functions h1, h2 and h3. Now again, this is an asymptotic response for the magnitude. The actual response is not this the same as this dark red line. In this case, if we actually plot the actual magnitude response, that is shown here in the purple line. So asymptotically on this side, the line converges to the red line. So this is the asymptotic response. The actual response is something like this. And at infinity, the red line and the purple line converge and meet. Another observation from this is that because the purple line, which represents the actual system response, is above the red line, it happens to be an underdamped system. And we will explore this more in our later lectures. So in this class, what we have covered till so far is a little bit about what is an overdamped, underdamped and critical system. Then we went into the area of phase and magnitude plots. We also understood what is the meaning of terms poles and zeros, poles being the roots of the numerator factors, zeros being the roots of the numerator factors and poles being the roots of denominators. And then we constructed phase and magnitude plots, and then we moved to Bode plots, and what we have covered today is how to construct a Bode magnitude plot for a transfer function which is a multiple of several small simple transfer functions. So this is what we have covered today. In the next class, we will learn how to construct Bode plots for the phase of the same transfer function. Thank you.